All right? And that is all we're going to say about this algorithm. And if you loved it, then what you should do is you come to 3101. And if you didn't understand it and you're thinking, how the hell am I going to handle this on the exam? It won't be on the exam. All right? All right, so what will be on the exam is I did like, we put on the homework assignment a question about the look-ahead 1 grammar and how that parses. I think that's a great algorithm that you should all be up for. I think this is a dynamic programming algorithm, and after taking a couple weeks of dynamic programming, I find about half the students can write a dynamic programming algorithm, and about half the students fail. Right? So I don't expect you to be able to do it right now. All right? But maybe it gave you some flavor, and it'll help you when you'll be processing it in your sleep. In fact, tonight you're all supposed to have scary dreams, right? Because it's Halloween. Happy Halloween, everybody. And you can dream about dynamic programming. All right? All right, so how are we doing for time? We go from 4 to 5:30, so we still have lots of time. Excellent. So, any questions about what we've done so far?
Yeah, what just happened?
What just happened with dynamic programming?
Oh, yeah.
It was a nightmare.
So, Professor, just to confirm, everything that said dynamic programming, all the slides that had the word dynamic programming in it, is not in the exam.
You're not going to make me say that twice, are you?
It's a good news, right?
It's being recorded, so you can listen, but you didn't hear me say that. All right, so context-sensitive grammars, just to fill out the whole topic of grammars. Chomsky, who invented all this stuff, also invented context-sensitive grammars. So context-free grammar has a rule that whenever you see a C, it doesn't matter how the C is appearing in the rest of the string. The context doesn't matter. You can replace it with an ABC, right? So that's context-free grammar. If you have a context-sensitive grammar, then the rule will be, say, whenever you see a capital C with the D, little d before it and little c after it, then you can replace this whole thing with that. And that allows much more power in our grammar. So here's an example, and it says you can replace the BCC with the ABCC, right? But if it appears in a different context, then you're not allowed to replace it, right? Does that make sense? And context matters. And so if you look in the books, sometimes context-sensitive grammars, they allow shortening rules, and sometimes they don't allow shortening rules. If you don't have a shortening rule, then the string that you're parsing keeps getting longer and longer. But we're gonna allow shortening rules as well, and then that gives us even more power. And in fact, we have as much power as doing a Turing machine. All right. So what we're going to prove now is what we're going to show is going to give you an example of a context-sensitive grammar, and then we're going to show how it's as powerful as a Turing machine. And I just remembered something I wrote on the board last time, so I should make a new slide and write it on the board now. So what we're trying to prove is that, right, if we want to prove that for every string, if the string is in the language, then the grammar generates it. And if it's not in the language, So here, this is your grammar can generate it. And of course, this is a non-deterministic grammar, right? You have a fairy godmother telling you which rules to apply. So if the string is in the language, then you can start from the start state, and you can use non-deterministic rules, and you can generate alpha. Yes. Completeness and soundness or something, if you want to do proof systems here. Right? It's funny, I know. That's another thing we can have nightmares about tonight, right? All right? So if it's in the language, then it can be generated from our grammar. And if it's not in the language, it can't be. All right? So let's see if I can remember to make that slide. All right, here, remember A to the N, B to the N, C to the N. Everybody here should know how to make a context-free grammar for this. Do you know how?
What?
A to the B, C to the A to the N, B to the N, C to the N. Is there a context-free grammar for this? No. No, you should know that you can't. I was pulling your leg. All right, why? Because this needs to be linked, and and these need to be linked, and these need to be linked, and they all cross over each other. Right? So
This is Halloween. This isn't April Fool's. You can't make a joke. You have to scare us.
no joke. Why? Did it scare you?
No, not really.
Not really. Okay, then. All right, I'll try harder. So, all right. So we're going to come up with a context-sensitive grammar for it, and it's going to be a pretty simple grammar. And as we talk about the grammar, we'll be focused on how the fairy godmother can generate any string that's in the language, any string that's had the form a block of A's, a block of B's, and a block of C's in that order with the same number of A's, B's, and C's. Then this grammar will be able to generate it. But then we'll have to argue a little bit that if the string doesn't have that form, then the grammar can't generate it. All right? So first, we start with our start symbol S, and you know we're going to get further down because we started so high, right? We spew out some number of 3 A's and 3 B's and 3 C's, right? We spewed out A, B, C 3 times, so we have 3 of each. And that's a good plus, that's good because we're going to need the same number of A's, B's, and C's. Right? You'll know that this A, capital A, is eventually going to turn into a little a, and a capital B is going to turn into a little b. But they have to be in the right order. Right? Right now, that we need to get the A's all together and the B's all together. All right? So we're going to give rules for the fairy godmother to use, and if she wants to, right, she can tell you to swap these things and putting all the A's together and all the B's together and all the C's together, right? So you keep swapping, and eventually you get them sorted, right? We're now focusing on the part of how the grammar can generate it, right? And later you'll see, well, it didn't have to sort them, but we'll see that if it didn't sort them, then it won't be able to finish. All right? So now we have them sorted. And now what we're going to do is S is going to turn into a little head, like a Turing machine head. And the Turing machine head is going to go through here, and it's going to turn the C's into little C's, and the B's into little B's, and A's into little A's. All right? So let's get our head here. First S is going to turn into T sub C, which is a C turning head. And what can this C turning head do? It can move. What it does is it sees a capital C to its left. It moves past it, and as it moves past it, it turns into a little c. Right? So this head is going to be able to move past it, and as it moves past the capital C's, it'll turn them into little c's. All right? Right? And then, once it's done all the C's, then there's a rule that'll change the C turning head into a B turning head. And then it'll move past the B's, producing little bees. Right? And then it turns into an A turning head, which turns all the A's into little A's. And then then at any point in time it wants to, right, an A turning head can disappear. Right? So there we produced a string. So you'll note this string has the form A's, B's, and C's of the same number. And so I hope I've convinced you that if it's in the language, the grammar can generate it. Yes?
Shouldn't we restrict the TC turns into TB only when there is DTC?
Well, okay, yeah, that would be a good way. You could have a B here, and then you only can turn when you're sitting next to a B. That would be a good thing to do, but it's not necessary here. So what we have to argue now is that nothing else can get generated. And why is that? Well, I guess I don't have any slides to talk about it. But suppose you don't, where can it go wrong? It can go wrong that it doesn't sort them properly, right? And then after you've converted the C's, you start converting B's, right? But then you can never convert C's again. If you don't convert all the C's while you're a C head, then those C's won't get converted, right? Because it never goes back to a C head. So you really, while it's a C head, you have to convert all the C's before you can go into being a B head, or else you'll leave capital letters around, right? And if you have capital letters, then you're never going to terminate, and you're never going to generate the string. Yes?
Like for the spewing and the sorting, is there like some way you tell it like when to stop doing the spewing, when to stop doing the sorting?
Well, that's the fairy godmother is going to be. So I guess I like to think about it as you have a good fairy godmother and a bad fairy godmother, right? When the string is in the language, the good fairy godmother is helping you figure out how to generate it. And when the string is not in the language, the fairy godmother is trying real hard to parse something to generate it, but she will be unable to, right? She's going to be the evil one and trying to figure out how to get, if there's a B and a C in the wrong order, she's going to try to get that, but there's no way she can get it. Does that make sense?
You said that there's no way for, let's say, once the T turning into the small B's, and it can't turn back into C's. How come you can't just add the extra rule saying, okay, I can turn back into C's if I see a capital C?
Oh, yeah, but that's not what we want. We want rules that can produce this and nothing else. That's the whole point, is our goal is that with these rules, if it has the right form, A to the N, B to the N, C to the N, then you can generate it. But if it has any other form, then you can't generate it.
Actually, this is non-deterministic.
It's definitely non-deterministic, right? Because you have...
It's bounded everywhere. There's no choice that you could make that would produce a...
Oh, you're saying it's deterministic?
Yeah.
Yeah, well, I guess the only non-determinism is how many times to spew this out. Choosing in is non-deterministic. And once you've chosen in, really there's only one way to go to terminate. Yes?
But the thing is like that you need extra rules for like the sorting and spewing. The turning one, like you don't need extra rules. You need extra like instruction for the spewing.
Instructions. Yeah, that's what he's saying, is that it's pretty much deterministic once you've done the spewing. All right? So, if you are interested on the homework assignment, this is a question on those practice homework assignments. And what it's asking you to do is to produce 2 copies of the same string. And it goes through and gives the answer. And the hint I've sort of had is it spews out like a palindrome, right? This is going to spew out alpha pound alpha reversed, right? And then they'll have this Q here, so you're going to get alpha pound and then this thing alpha reverse with brackets around it and a Q. And the Q will sweep around and reverse this thing. All right? But I figure we've covered one sort of example already, so I'm not going to cover this example, but it's in the notes if you want to see it. The reason we're talking about it now is because we're going to need it as a subroutine for what we do next. All right, so that's Chomsky again. You should definitely watch some of his videos. And now we're going to get into some other confusing things which we're going to cover later. And right now you can just remember it for the first time. So there's a difference between computable or decidable versus acceptable and enumerable. Right? If it's computable, decidable, then when it's a yes instance, the Turing machine must halt and say yes. And when it's a no instance, that's up. When it's decidable, and if it's a no instance, it may run for. It has to halt and say no. So decidable, you always have to stop, no matter what the input. You have to stop and give the right answer. All right. But up here in acceptable, the rules are slacked. So if it's a yes instance, you have to stop and say yes. But if it's a no instance, you can run forever. So the one example is the halting problem. Right? The halting problem you have a machine halting, and it's given as input another machine, an I, and what it does is it simulates M on I, and if M halts, then halt. So the halting problem is a yes instance if M halts an I. And you'll see that this algorithm, if M halts an I, then M halts. Right? But if M doesn't halt, then this program doesn't halt. Right? So that's an example. That's why the halting problem lives in this sort of world up here. Everybody sort of follow that? And yes?
You said that Turing machines can't solve the halting problem, and yet the big purple circle and the halting problem falls under acceptable / enumerable, which is also in little brackets of Turing machines?
Yes. You are absolutely right. Would you like me to clarify it again?
Wait, no.
The difference is these Turing machines must always halt. And these Turing machines only have to halt on the yes instances.
So technically the halting problem can be solved by Turing.
It can't be decided by a Turing machine. It can be accepted by a Turing machine.
It says something about the Turing machine class is equivalent to the Java program class in terms of compute distributed.
Yes.
So
Yeah.
Sensitive grammar is more powerful than a Java program.
Yeah, but the problem with the Java, the reason we put context-sensitive grammars up here is because they also can run forever, right? On yes instances, they halt. But on no instances, they're one non-deterministic, and on no instances, they might run forever, right? So that's kind of why they live up here. It's not really all that much practical. Practical is things here that if the answer is yes, then it says yes, and if it's no, it halts and says no. Having your program run forever isn't all that useful. So the whole purple circle is a bit esoteric. Not that the whole picture is not esoteric, but the purple is even more esoteric. levels of esotericness. All right, does that kind of make sense? Anyway, I wanted to say that context-sensitive grammars, where they fit in the hierarchy, and so we had to define the hierarchy, and they sit way up here. All right, so, yeah, and this is how I sort of said that context-free grammars the context-sensitive grammars, they can halt, or they could crash, or they could run forever. And that's why it's purple. Right? On no instances, they might run forever or halt with non-terminals. All right, so what we're going to do now is you give me a Turing machine, and I'm going to give you a context-free grammar. Context-free grammar. No, that's supposed to be an S here. Another typo. Everybody marking all those typos that I'm going to have to remember? Context-sensitive grammar, such that what the grammar can generate is equal to what the Turing machine accepts. Alrighty, so we're going to be simulating this Turing machine. All right, so we have to somehow write down what the Turing machine is doing. And so we're going to encode it as a string of terminals and non-terminals. So we start with just the tape, and we mark the beginning and end of the tape. So here's the contents of the tape, and we mark the beginning and the end of the tape like that. And then we have to have marked what state the thing is in, and for every state, we're going to have a non-terminal capital Q representing that state. And we have to mark the head location, right? And how do we mark the head location? Well, we just put the state where this means this is the contents of the tape, and the head is on this character, the character past the Q, and we're in state QI. All right, and so, in fact, I have a slide in a minute which shows that this is the notation Sipser uses in his book anyway. So if any of you are reading, actually that's a good question. Are any of you reading the books? No. Is anybody reading it and finding it? You guys are reading it, are you finding it useful? We got two usefuls back there. All right, so which one are you reading? Sipser? Excellent. All right, people understand this notation? This is the notation Sipser uses. Yes?
How is spewing done on a tape?
That question hasn't gotten up yet here, so why don't you wait until we have that question. You're kind of jumping pages and pages ahead. I'm just saying, how does this relate to the Turing machine state? All right, let's keep questions on the slide in question. Your question on the slide in question?
The head location.
Yes?
Yeah, so QI. You're saying that QI is what the head is looking at to the right of it.
Yeah, the guy to the right is
So therefore, it's going to start actually before the 1 and end before that final 0.
yeah, if it's looking at the 1, it'll be here.
And when it finishes, it's going to look...
If it's looking at the first blank, it'll be here. Right? All right. So now, let's come up with some grammar rules. So suppose that the Turing machine is in this configuration, and we have some delta rule, and the delta rule says, hey, I'm in state QI, I see a 1, what do I do? Well, here the rule is saying, if I'm in state QI and I see a 1, what do I do? Well, the rule might say, write QJ. All right, so we're gonna change that to a QJ. It says change the 1 into a C. Right, so you change the 1 into a C, and then it says move the head. So you swap the C with the Q. Everybody see how what we did is we went from this to to this.
What's the swap happening?
The swap, this C that used to be a 1 is swapping with the Q, because now we're looking at this one.
Swap in there.
What?
I mean the swap in there. Like where's that swap happening in there?
The head moved. Let's do it again. All right? We observe that we're in QI and we're looking at a 1. Right? So what do? We turn from QI to QJ. We change the 1 that we're looking at into a C. And then we move our head right, which swaps the C and the Q. Right? So what's the rule? The rule says you can change QI1 to being CQJ. Right? That's the context sensitive rule. You see how it's just mimicking the movement of the head of the. We change states and we move the head. Everybody kind of follow that? So now it's a little harder when we move left. So if we move left, then we change to J. We write the 1 turns into a C, and now the Q swaps with the 0 before it. Right? So the 0 before it swaps. So the rule actually changes 0 QI1 into QI 0C. Yeah.
So in that grammar, right?
Yep.
That's being swapped. I see that. But in that thing, it just moved. The header just moved to 0.
Yeah, because the rule says if you're in QI and you see a 1, it's a Turing machine. The head was here. Let's sort of do it again. Right? The Turing machine says that if the head is looking at a 1 and you're in state QI, then what should you do? You should first change to state QJ, and then the 1 that you're looking at, which is right in front of the Q, changes to a C.
That I understand. But then the swap thing
So-
doesn't have any relevance to the Turing machine.
Yeah, it does, because watch, the head is going to appear, and it's going to move over. Right? The head moved here, and now where is the Q supposed to be? The Q is supposed to be before the 0. Right? We swap these two things to move the oh, I haven't done the swap yet. The swap's coming now. Right? I moved the Q before the 0. Right? Does that make sense? And so the rule is going to change these 3 things into those 3 things. Yes?
Make a rule for every possible character, like in the alphabet of the Turing machine?
Every entry of the Turing machine.
When going backwards, like you need one for one.
Oh, listen to him. He gets a gold star because we need this one as well. Right? Because this could have been a 1 here. Well, I mean, the character before is either a 0 or it's a 1. So either we move past the 0 or we move past the 1.
We have it as much rule. We have twice as much rule.
Twice as, yeah.
States.
Yeah, so there's twice as many rules as there are entries in this table. Yeah. Well, there's twice as many rules here as there are states, and then there's twice as many, so it's going to be 4 times as many, but 3 times as many, because anyway, some numbered. All right, so this is just Sipser saying, when Sipser describes the Turing machine, and he described it in this exact way. So if you're reading Sipser, that's what you would have gotten out of reading Sipser. All right, so now we have to compare the Turing machine and the grammar, right? The Turing machine kind of starts looking like this, right? And it goes through the computation, and it ends looking like this. So by the way, we're going to assume that the Turing machine erases everything on the tape with blanks before going into the accept state. All right? So this is what it looks like when everything is blank except, right? And we're at the beginning of the tape. So that's what the Turing machine is going to do. And what does the grammar do? The grammar is a lot, and this is a deterministic Turing machine. It could be a non-deterministic one. It doesn't matter. I just said it could be a deterministic. But this here is definitely non-deterministic. We start from S, and what do we want to end up? We want to end up producing the string in question, right? So it feels like we're going backwards, right? So what this grammar is supposed to do is non-deterministically be able to generate any string that this Turing machine would accept. Right? Everybody good with that? It basically says, right? If the grammar can generate it, so if the Turing machine accepts it, then the grammar can generate it. And the Turing machine doesn't accept it, then the grammar can't generate it. Right? So how is our grammar going to go? Well, first thing it's going to do is it's going to non-deterministically guess what the string is. All right? It's going to guess that. And then it's going to use the same rules, the same thing that we did, remember, on the homework assignment that we didn't cover. It's going to produce alpha, this start stuff, alpha. It produces 2 copies of alpha, right? And it does that by spewing and then rearranging. Everybody kind of buy that? You here with me? So one thing that's funny is there are various things that I say all the time, like, do you buy that? And my sons and my ex-girlfriends all laugh that they pick up Jeffisms. They call them things that Jeff always says.
We did the same.
Sir, when you spewing, so is there a blank in between, or it's just the AQA?
I think what we're doing is we spew out this stuff, and this one will be in reversed, and then you plop this in the middle, and then you have to attach this on the end, and then the Q moves and reverses this thing, and then we're ready to go. So anyway, let's not worry about how we get this. That's a homework assignment. You can read the homework assignment. All right? Somewhere in the homework assignment, you're able to generate alpha alpha. All right? And now once we've done that, right? See the assignment how to do that. It even says it. Right? Now we want to be able to have as many blanks as you want. So we can add blanks. And the rule to add blanks is whenever this is the end guy, you can stick as many blanks in there as you want. Right? And then you want to run this Turing machine. Right? You run the Turing machine with the transitions like we've talked about before. And it'll keep doing it until it gets into an accept state. But as I said, it blanks off the tape. Right? And now we have the one rule that's a shortening rule. All these rules so far made things longer. The one shortening rule is to get rid of the blanks. All right? So you remove the trailing blanks. And we're going to hit the punchline in a second, then I'll come back to you. So here now we have, if you put alpha alpha, and if this alpha is accepted, right, then you get in this format. And now, when you have this format here, that thing can just disappear. Right? Here's another shortening rule, which says, oh, that's removing the blanks. How did we remove the blanks? Great. And then, how do you accept is this last thing disappears, and you're left with the alpha that was accepted. Does that make sense? We had a question in the back first.
Is there any reason why there's no blanks before the head? Before this
Yeah.
on one side.
Well, the general assumption about a Turing machine is that it's one way in one direction, and the head starts at the beginning, and there are no blanks to the left.
Yeah. Well, a lot of times we like go back and forth. Like let's say the palindrome one, we go to the beginning.
Yeah, that was me saying maybe this is well, one, you can define your Turing machine. Generally, the Turing machine starts somewhere and doesn't have blanks to the left. And I guess I was having blanks to the left so that it didn't really matter if things shifted a bit, and I was thinking about it as a subroutine for a bigger task.
Okay. But generally, we don't do that.
Generally, you don't have blanks at the beginning.
Can you open it again? I just don't know where to add all the blanks.
All right. Do you have another question before I go over it again?
Yeah, speaking of the blanks, how can we go through the trouble of adding them at the end and then only to remove them?
All right, let's answer all of those questions. We start with the start symbol producing alpha alpha, and this is the format that mimics what the Turing machine looks like, right? And then this alpha just sits here. Well, for the Turing machine to run, sometimes it moves its head to the right, and so we don't know how far it's going to go to the right, but wherever it goes to the right, we need to give it as many blanks as it wants.
So we assume there's going to be blanks after.
Yeah, after the input, that's what the way the Turing machine starts. Is it starts with, it's a one-way infinite tape. It starts with the input at the beginning, and to the right of the input is infinite blanks. So those blanks will appear as needed, and the Turing machine will run. And then when the Turing machine finishes doing what it does, is it blanks off the tape and goes into accept state. So there'll be some number of blanks that it has used, but it's blanked them. Right? Why did we need them? Well, because it wrote things here. But eventually it finishes writing them, so it erases everything. It cleans up after itself.
Cleans up the input.
Yeah, it cleans up the input. It cleans up any garbage that's written there. Yes?
How exactly do you blank out a blank?
Well, if it's already a blank, then you don't have to blank them out. But if this blank got written to as ones and zeros, then you have to blank them out again before. You have to turn everything back to a blank. Yes?
Could we use something non-terminal that erase himself with an undeterministic thing? Like a capital B, and at the end, capital B can go to the void.
Yeah, this is kind of like this is erasing the blanks. I think this is kind of what you mean. This is our blank eraser at any rate, right? You can. What we're imagining is that there's an infinite number of blanks there, and so this rule can give them to you when you need them, and this rule can take them away when you don't need them. Yeah.
For the transition, the QJs become the QIs?
Well, this is whatever the transitions of this lists all the transitions of your Turing machine.
Ah, okay, so it's just like...
It's just a few little examples. It's really all the rules of your Turing machine are written here. Right? Does that make sense? Yes?
Just accept the input, right?
Yeah. This is an accept. This is saying if the Turing machine accepts, then the grammar can generate it.
Professor, can you go again, how do you get rid of the second alpha again? The second alpha, the right side alpha. 1, 0, 1.
This guy over here?
No, the second line, this one.
This one?
No, the right side one.
This one.
That's what you're erasing, right?
Well, the Turing machine, what the Turing machine is, the rules of the Turing machine is it starts on a one-way infinite tape with the input there, and when it finishes, when it knows the answer, that it's an accept or reject, then what it does is it erases, it blanks out the entire tape, right? And so where it starts in this sort of format, and when it accepts, it's going to look like this.
Oh, and it goes back. Oh, it's a Turing machine.
Yeah, this is the Turing machine running here. This is these Turing machine rules.
Yeah, I forgot.
These Turing machine rules are running us from here to here. Right? You have to write the Turing machine to do that. All right?
You said that when Turing machine accepts it, then it's part of the grammar?
Yes. And then here, suppose the Turing machine rejects it or runs forever. well, then you'll never get rid of the Q, right? The only way you can get rid of the Q is by having it be an except Q, and you remove the except Q, right? There was that rule here which will remove the except Q. Right? So that says if the string is not in the language, then the Turing machine doesn't halt and accept it, and so the grammar can't generate it. And that is it for these slides, guys. And that's it for our day. So it was a good day. And have a happy Halloween. I hope everybody